All right, second video is going to be on kinetics, is going to be on reaction profiles, energy diagrams. You might hear them called different things, but it's looking at the energy of a reaction over time. So here's an example of a reaction profile. It shows the change in potential energy throughout the course of the reaction. So the x-axis is, they might call it the reaction coordinate or course of the reaction, or you can think of it as like time. So as the reaction goes, what happens to the energy? And you will notice that in this case, this beginning part shows the energy of our reactants. This end part shows the energy of our products. So the difference between the reactants and the products is our change in energy throughout the reaction. We will call that delta H later, the heat of the reaction. And you will notice that when you go through these reaction profiles, they always go up before they go down, and this initial distance up is what we call the activation energy, and that is the amount of energy required to start the reaction. A reaction will always require an input of some energy to get it started, so you'll always go up before it goes down. And then this peak point we call the transition state, so that's that high energy state where you're in between being a reactant and being a product. So some of your bonds are breaking, you're forming some new bonds. That in between is called the transition state. It's different from an intermediate, which we will talk about later. So transition state, different from intermediate. And you will notice that, so again, the heat of reaction is the difference between the reactant's energy and the product's energy. In this previous reaction, we saw that the products were lower in energy than reactants. That means some energy was given off, so we would call this an exothermic reaction. This example is an endothermic reaction because the products are higher in energy than our reactants. So there's been a net input, a net gain of energy. And so we'd say this has a positive delta H, the heat of reaction. So here's an example of that side by side. You can see an exothermic reaction, endothermic reaction. Exothermic's releasing energy, so products are lower than reactants. Endothermic is absorbing energy, so products are higher than reactants. The one on the right, endothermic, will have a positive delta H. The one on the left will have a negative delta H. The activation energy, like we mentioned, is the amount of energy required to get a reaction started. So for example, reactions we typically think of as being very exothermic, like burning, right? It's like combusting a fuel. It's a very exothermic reaction. That flame we think of as releasing heat energy. But in order to get that reaction going, you need to light it with a match. So we need to have an initial input of energy to get the reaction started. And that energy is what we call our activation energy. And this goes back to what we said earlier, that not all collisions will result in a reaction. So in order to get a reaction to occur, the reactants need to bump into each other, and they need to bump into each other with enough energy to overcome that activation energy hump. So this is an example of a collision that does not have enough energy to react, and you will see that they don't have quite enough energy to make it up and over that hill. So they're just going to go back to where they started and stay as reactants. In order for reaction to occur, those molecules need to bump into each other with enough energy to get up and over and all the way down to the other side, to the product. Here's an example. You can see why increasing the temperature will help make a reaction go faster. So this is what we call the Maxwell-Boltzmann distribution, showing the particle speeds. And this is an important graph to be able to interpret. And you will see that the temperature is related to the average kinetic energy of your molecules. This is our x-axis is kinetic energy. So as the temperature increases, you'll see how your curve shifts over to the right. So let's say this point right here is the activation energy for a given reaction. It's the minimum energy required to react. As your temperature of your sample increases, you're going to have a greater percentage of particles that have the energy required to get up and over, this hump right here we were talking about. So when you increase the temperature, you're going to increase the energy these individual particles moving around, so more of them are likely to have collisions with enough energy to get them up and over this curve. So again, this is showing the number of molecules and their kinetic energy. In a higher temperature sample, you've got a greater percentage of those molecules have the energy to react. So that's why that will occur faster at a higher temperature. And here's another picture showing the same idea. So remember with temperature, we've got two things going on. The molecules have greater kinetic energy, so they're more likely to have that activation energy in order to react, and they also will collide more often. So you've got two things making your reaction going faster. They're bumping into each other more often, and they're bumping into each other with more energy. And I'm going to skip past that one. So transition state versus intermediate. I mentioned before that they are different things, and we'll talk about intermediates when we get into reaction mechanisms, but I wanted to point out two examples here. This is a one-step reaction going from reactants to products, and that peak part there in the middle is called the transition state. Sometimes you will have reactions that have two-step mechanisms or even three-step mechanisms, and this is what a reaction profile would look like for a two-step mechanism. You'll see that each step in the reaction has its own activation energy. It's got its own hump that it's got to go over, and this part there in the middle is the energy of the intermediate. So we've got reaction number one goes from reactants to intermediate, then step number two goes from intermediate to products. And these two peaks right here are your two transition states. This is transition state for step one, transition state for step two. This low part here is the intermediate that's formed in that two-step mechanism. And again, notice how these are both exothermic reactions. The products are lower in energy than the reactants. Another thing to point out with this curve right here is you can see that the first step has a much higher activation energy than the second step. And the higher the activation energy, the less likely you are to have an effective collision, with enough energy to react. So reactions with higher activation energies will occur slower. So if you're looking at this two-step reaction mechanism, it would say, well, this first step is going to occur slower than the second step, because this first step has a much higher activation energy. So if we're thinking about rate laws and reaction mechanisms, this first step is going to be your slow step, because it has a greater activation energy. So it's going to occur slower. This second step looks like it's going to occur pretty fast, got a very small activation energy. Okay, and this is a picture of what I was just talking about, is that the one of the things that will affect the rate of a reaction is what the activation energy is. So if you're comparing two reactions, the one with a lower activation energy will occur faster. And that is because the energy required to react is lower, so you're more likely to have a collision that has enough energy to react. If you're comparing two samples, the same temperature, same concentration, so all other things being held equal, the one with the lower activation energy will react faster because we've got a lower threshold energy required. Okay. Another way of putting it, the larger percentage of reactants in a given sample will collide with a sufficient energy to react. And thinking about catalysts and how those change things, catalysts act by lowering the activation energy. So catalysts, notice when you add a catalyst to a reaction, you're not changing the reactants, you're not changing the products. What you're doing is you're changing that transition state. So we're getting from point A to point B by a different mechanism, and that new mechanism requires less energy than your previous one. So the catalyst makes that path easier. It does that by lowering the activation energy. And so, again, now you're more likely to have collisions with enough energy in order to react because you've lowered that minimum threshold. So you've made it easier for the reaction to occur, so it will occur faster. So here's an example, again, showing those Maxwell-Boltzmann distributions. So if you're thinking you have a sample of molecules at a given temperature, this is your kinetic energy, that's your number of molecules. You'll notice in a reaction with let's say your original reaction with no catalyst this is its activation energy, and for this sample of molecules, only these molecules right here are going to have enough energy to actually react when they collide. If you add a catalyst, you lower the activation energy, and so now, without changing the temperature of my sample, I all of a sudden have a lot more molecules that have enough energy to react. So that's how lowering your activation energy will speed up the reaction right there. And again, catalysts can change reaction pathway as well. So they might change a one-step reaction to a two-step reaction. And notice on this two-step reaction, both of the steps have lower activation energies than my original reaction. So again, they will occur faster than my original. Here's another example of that, showing a catalyzed versus uncatalyzed reaction, where you're changing it from a one-step to a two-step reaction. And then here's yet another one, involving an enzyme. So key thing is catalysts speed up the reactions by lowering your activation energy required to get the reaction going.